Imagine a microscopic payload that could fundamentally accelerate human healing.
Right.
It's packed with specialized proteins and RNA, and I mean, it's basically considered the holy grail of regenerative medicine.
Oh, absolutely.
But there is this massive catch for anyone trying to use it. It comes with a brutal, totally invisible self-destruct timer.
Yeah, that timer is unforgiving.
Right. So once you actually prepare this payload, you might have just 2 hours, and sometimes only 30 minutes, to use it before it just degrades into useless biological debris.
Which is a logistical nightmare for clinics.
Exactly. So today on this deep dive, we are unpacking the strict ticking clock of exosome preservation. Specifically, we're looking at the intense battle to keep these nanoscale messengers biologically active on a clinic counter before they actually get administered to you, the patient.
Yeah, it really is a constant battle against physical chemistry. I mean, exosomes are incredibly tiny, only 30 to 150 nanometers in size.
Wow, that's small.
Extremely small. And their entire function in the body relies on moving from one cell to another to coordinate tissue repair. But the second you isolate them outside of their native physiological environment...
Like putting them in a vial.
Right, exactly. The moment they go into a vial, you are fighting temperature, you're fighting structural stress, and you're fighting time just to maintain their integrity.
And we brought quite a stack of sources today to figure this out. We've got manufacturing manuals, clinical storage guidelines, some cutting-edge biophysics research on cellular release, and even a wild new Chinese patent on preservation gels.
Yeah, that patent really flips the script on how we handle these things.
It really does.
Yeah.
But before we map out the timeline of preparing exosomes for use, we kind of have to look at what we are actually trying to protect. Because functionally, exosomes are acellular, right?
Yep. They are not alive.
Right. They are secreted by live cells, like mesenchymal stem cells. But they don't contain live cells themselves. They don't respire. They don't metabolize.
They're just the messengers.
Yeah. So, I mean, if we aren't trying to keep a cell alive, why are they so insanely difficult to store? Why can't we just put them on a shelf in the clinic?
Well, it comes down to their architecture. Their bioactivity, which is their ability to actually deliver a therapeutic effect to you, relies entirely on two very fragile structural components.
Okay.
First, you have the integrity of their phospholipid bilayer membrane. And second, the preservation of the signaling payload inside that membrane, which is all those growth factors and microRNA.
So they're like microscopic water balloons.
That's a great way to put it, actually.
If the balloon pops or leaks, the message is lost.
Exactly. And the thing is, if you store exosomes in a standard liquid solution in just a normal 4°C refrigerator.
Like a standard lab fridge.
Right. If you do that, the lipid membrane undergoes a phase transition.
Meaning the lipids go from a fluid, flexible state to a rigid, sort of gel-like state.
Yes. And that rigidity introduces physical defects. The membrane basically starts to leak. Research shows that after just 1 month at 4 degrees, you see an almost complete degradation of vital exosome markers.
Oh, wow.
Just 1 month.
Yeah, proteins like TSG101 and HSP70 just vanish.
Which means the exosome loses its entire mechanism for action. Because TSG101 is critical for the exosome to properly dock and interact with the target cell.
Right.
And HSP70 is a chaperone protein essential for cellular stress signaling. So if those vanish, you essentially just have a blank, empty lipid envelope.
An envelope that can't communicate with anything.
Right.
And to make matters worse, the particles begin to stick together. Minor pH changes or temperature fluctuations cause aggregation.
They clump up.
Exactly. And once they clump, the RNA inside degrades, and your therapeutic exosome is totally compromised.
So this thermodynamic vulnerability is why the industry relies so heavily on lyophilization, right? Freeze-drying them to make them shelf-stable.
Yeah, that's the primary workaround. By freezing the preparation and sublimating the water out under a vacuum, you create a dry powder. Right. And the clinical manuals we looked at indicate lyophilized exosomes can be stored between 2 and 8 degrees Celsius for up to 2 years without functional compromise.
2 years is great for shipping and storage.
But to actually administer them, you have to reconstitute that powder. You add a buffer, like 1x ppb or deionized water, and you have to let the vial sit at room temperature for 5 to 10 minutes to let the pellet dissolve completely.
And that reconstitution phase is where the structural stress of the entire process is suddenly unmasked.
Because you're adding the water back in.
Right. Lyophilization is convenient, sure. But removing water from a lipid membrane that fundamentally relies on hydrophobic and hydrophilic interactions to maintain its shape It is immensely traumatic to the structure.
Oh, I see. But manufacturers use cryoprotectants, right? Like trehalose.
Yes, they do. The sugars replace the water molecules. They hydrogen bond to the lipid head groups to form a sort of glassy matrix. It locks the bilayer in place while the powder sits on the shelf.
But the moment you add your PBS to reconstitute the vial, you dissolve that glassy matrix.
Exactly. You wash away the protective scaffolding, the phospholipid bilayer wakes up, and it is highly stressed.
Mm.
It becomes incredibly susceptible to rapid aggregation, and it starts shedding those functional surface proteins.
It's basically like making instant coffee. Once you add the water, you can't put the powder back in the jar, and the clock is ticking.
That is spot on, and this triggers the biological countdown. The guidelines are absolute on this. Reconstituted exosomes must be used within 2 hours to ensure bioactivity.
2 hours, wow.
The clock literally starts the second the liquid hits the powder.
I mean, if they're stable for 2 years as a powder, it's wild that they suddenly have a 2-hour self-destruct timer once rehydrated.
Well, you have to remember, retaining protein content on a lab test 3 hours later is not the same as retaining biological activity.
Right.
The proteins might still technically be floating in the vial, but if the exosomes have aggregated or the bilayer is damaged, the signaling payload is no longer bioavailable to your cells.
So what happens if a clinic manages to only use half a vial within that 2-hour window?
The standard protocol dictates you have to aliquote the remaining solution and freeze it immediately.
Right, and you have to be careful how you do that. Because these lipid bilayers are inherently sticky, if you put them into standard plastic, you're going to lose half your yield directly to the walls of the tube.
Yeah, you absolutely have to use low-binding polypropylene vials.
And even then, your freezing protocol has to be flawless. You can store those aliquotes at minus 20 degrees Celsius for a month, or minus 80 degrees for up to 6 months. But you must strictly avoid repeated freeze-thaw cycles.
Right, because every single transition between solid ice and liquid shears the vesicles. You rip them apart.
Ouch. So if the freeze-drying process introduces so much osmotic trauma to the lipid bilayer, it makes total sense why some clinical labs like Nova Vita Labs refuse to dehydrate them at all.
Yeah, many purists opt for the liquid alternative.
Storing the acellular exosomes in their native state at ultra-low temperatures, usually minus 80 degrees Celsius.
Deep cryopreservation avoids the dehydration trauma entirely. It perfectly maintains the native exosomal membrane integrity and the stability of surrounding elements like hyaluronic acid.
And you don't even need to cryoprotectant additives.
Exactly. It provides a much cleaner, biologically representative product, but it shifts the burden directly onto clinical logistics.
Because of the thawing process. The thawing alone is a massive bottleneck. You have to let the vials sit upright at ambient room temperature, around 20 to 25 degrees Celsius, for 5 to 10 minutes.
And no shaking. The guidelines prohibit any agitation, vortexing, or the use of direct heat blocks.
Right. Why are heat blocks so bad for them?
Because using a heat block or a warm water bath causes rapid, uneven thermal expansion. You will literally shear the bilayer or denature the signaling proteins before the ice core has even finished melting.
Oh, wow.
Yeah, it has to be a slow, ambient thermal transition.
But here is the crazy irony of skipping the freeze-drying process to keep them more natural. It actually shrinks your working window.
Significant.
With the reconstituted powder, we had 2 hours. But once these ultra-cold liquid exosomes are fully thawed, the protocols mandate they be used promptly, ideally within 30 minutes.
30 minutes. That is the ultimate trade-off in exosome therapeutics right now.
I mean, how can clinics realistically manage that incredibly short time frame?
It requires extreme precision. You cannot begin the ambient thaw until the patient is literally prepped and ready in the chair, because refreezing a liquid native exosome is strongly discouraged. It's going to introduce those ice crystals and shred the membrane.
So lyophilized gives you easier shipping and a 2-hour window, but risks altered bioavailability.
Yeah.
And liquid at minus 80 gives you a cleaner product, but requires an intense cold chain and a frantic 30-minute sprint.
That's the dilemma.
Which perfectly explains why there's this massive push to hack room temperature storage entirely. And that brings us to the Chinese patent we found.
Right, patent CN1168979222A. It represents one of the most creative biophysical approaches to this exact bottleneck. They completely rewrite the rules of exosome storage.
So instead of freezing them, they outline a method where they mix 0.1 to 0.5% pectin and sometimes sodium alginate with a phosphate puffer.
And then they heat it.
Right, to 60 or 80 degrees Celsius, which forms this thick colloidal gel. Then they let it cool to room temperature, and they add fresh milk exosomes into it.
And the results are incredible. The data shows these exosomes maintain their typical cup-shaped structure and critical biological markers at room temperature for 28 days.
28 days, that's practically a miracle compared to 30 minutes. It's like encasing the exosomes in microscopic jello.
That's a really accurate way to visualize it, and they specifically track the CD9 marker, which is a tetraspanin protein.
Why is CD9 so important here?
Well, CD9 facilitates cell fusion. If CD9 degrades, the exosome cannot integrate with the target tissue. It's useless. So maintaining it for 28 days without ultra-low temperatures or lyophilization is a staggering leap in preservation technology.
The patent actually specifies the exact mechanism making this possible. It says the pectin gel keeps the solution's zeta potential absolute value above 30 millivolts.
Yes, zeta potential.
What exactly is zeta potential? And why is 30 millivolts the magic number for keeping these things alive for a month?
So, to put it simply, zeta potential measures the electrical charge of the particles in a liquid suspension. Every exosome naturally carries a slight negative electrical charge.
All right.
If that charge drops close to zero, there is no repulsive force between the particles. So, just random Brownian motion causes them to bump into each other and they aggregate.
And clumping leads to membrane rupture.
Exactly. But an absolute value over 30 millivolts means you have engineered a highly stable suspension. The exosomes carry a strong uniform charge, so they act like opposing magnets. They strongly repel each other.
So this physical distancing prevents the aggregation cascade entirely.
Yes. The pectin chains wrap around the vesicles, and the sodium alginate forms a protective film that actively prevents the surface proteins from denaturing. The colloidal gel basically provides a structural and electrical matrix that simply pauses the degradation clock.
A 28-day shelf life at room temperature fundamentally changes the accessibility of regenerative medicine. I mean, it eliminates the expensive cold chain shipping and removes that frantic 30-minute administration countdown.
It would completely change the clinical workflow.
It really would. Now, we've looked deeply at how temperature dictates storage parameters in a lab. But a landmark 2023 biophysics study by Mahmoud reveals something amazing.
Oh, this study is fascinating.
Temperature plays an even more profound role in how cells naturally release exosomes inside the body. Mahmoud shifted the focus from preservation to cellular biogenesis.
Right. This study investigated how temperature acts as the master regulatory switch for exosome secretion.
They used this really advanced live cell imaging with a fluorescent marker called CD63 fluorine.
That tag is brilliant.
It is, because it remains totally dark while the exosome is trapped inside the acidic environment of the cell. But the exact microsecond the exosome fuses with the outer cell membrane and enters the neutral pH of the extracellular space, it flashes green.
Yeah, it allows researchers to quantify the exact rate and timing of vesicle release in real time.
And what they found was wild. At normal physiological body temperature, 37 degrees Celsius, the imaging shows cells lighting up constantly.
The secretion rate is rapid.
Yeah, and the exosomes immediately disperse away from the cell into the surrounding space. But when they lower the ambient temperature to 23 degrees Celsius, which is roughly room temperature, the entire biological conveyor belt jammed up.
The secretion rate just plummets. But more critically, the release mechanism itself becomes fundamentally impaired.
Right, because the exosomes reach the surface, the initial fusion happens, but they do not detach. The fluorescence just lingers there.
Exactly. They remain physically tethered to the fusion site on the cell surface. They don't fully pinch off.
Why does that happen?
It's tied to the thermodynamics of the snare proteins. Those proteins mediate that final membrane fusion and release mechanism. At 23 degrees, the lipid membrane is less fluid, and the enzymatic cleavage required to finalize the release simply doesn't happen efficiently, so the exosome remains stuck.
Wait, if lower temperatures cause cells to hold onto their exosomes, are researchers accidentally ruining their own yields just by handling cultures in a chilly, air-conditioned lab?
That is the exact implication, yes. Handling cells at room temperature fundamentally alters secretion rates. It leaves a vast percentage of your therapeutic product stuck to the cell wall.
Oh, wow.
So when you harvest the surrounding media to collect the exosomes, your yield is artificially suppressed. The data confirms that to maximize yield, the ambient temperature must be strictly maintained at 37 degrees right up until the exact moment of harvest.
It just reinforces how exquisitely tuned these biological messengers are to their environment.
Absolutely.
So, for you listening, whether you are a patient receiving cutting-edge regenerative therapy or a researcher in a lab, the core takeaway is you have to respect the physical parameters.
The ticking clock is real.
It really is.
Yeah.
If you are working with lyophilized, reconstituted exosomes. The moment you introduce that buffer, your 2-hour timer at room temperature begins.
And if you are thawing ultra-cold native liquid exosomes, that gentle ambient thaw gives you exactly 30 minutes to administer the payload before thermodynamic degradation ruins the therapy.
It's all about that clock. But we spend so much time engineering cold chain logistics to pause this biological clock. The Mahmoud study kind of offers a fascinating glimpse into the future.
How so?
Well, if our own cells naturally hold onto their exosomes at cooler temperatures and then rapidly secrete them when the localized environment reaches 37 degrees, could we eventually manipulate the body's own thermostat?
Oh, I see what you mean. Using localized thermal triggers to command native exosome release inside the body.
Exactly. Instead of manufacturing and injecting an exogenous payload within a frantic 30-minute window, what if you applied localized, precise heat to an injury site like a torn tendon?
You could theoretically signal your local cells to flood the area with their own regenerative messengers.
Right. It reframes temperature from a frustrating logistical hurdle into a direct, targeted therapeutic tool. Something to think about the next time you use a heating pad.
That is a really incredible concept to explore.
It really is. Well, that wraps up our look at the strict biological countdown of exosomes. Thanks for joining us on this deep dive, and we'll catch you on the next one.